So, last class we were talking about fault simulation, and if you recall, we had talked about two algorithms for fault simulation, namely the parallel fault simulation and the deductive fault simulation. So, today we will be talking about another fault simulation algorithm, namely the concurrent fault simulation, which is somewhat similar to the deductive fault simulation in the sense that here also we are maintaining a fault list and we have some mechanism of propagating the fault list, but there are some differences as compared to deductive fault simulation. Well, in the method of concurrent fault simulation, the basic concept is that we try to take advantage of the fact that most of the time during simulation, say given a circuit with certain number of inputs, we apply a test vector. Okay. Possibly we can inject a fault in the circuit and simulate with respect to that. Then from one test vector T1 we go to another test vector T2. But actually what happens in practice is that if you look at the circuit, only a small portion of the circuit will have some changes with respect to the logic values of the lines. The remaining portion of the circuit will not be affected in general. Okay. So, the idea we are trying to take advantage of is that most of the time during simulation, most of the values in most of the faulty circuits agree with the corresponding values in the good circuit. Say with respect to two faults, maybe the values will differ in those local portions of the circuit where the faults have been injected. The remaining portion, the logic values may be all same. Okay. So, we try to take advantage of this fact, and what we do? We simulate the good circuit N. Simulate means we do a true value simulation, we find out the logic values, and for every faulty circuit we call it NF. If F is a fault, we call the corresponding faulty circuit NF. Now, for the faulty circuit NF, we do not simulate the entire circuit, rather we only simulate those gates or elements in that circuit for which some input output values are different as compared to the fault free ones. Okay. This is the basic concept. Now, in the method of deductive fault simulation, what we did? We actually composed some fault lists which consisted of the faults which are actually getting detected, and there was a mechanism of propagating the fault list from the gate outputs to the next gate input, from there to the gate output again, using some simple rules based on set theory. But in contrast, in concurrent fault simulation, we are actually simulating the gate, we are evaluating the gate, and the fault list will not only consist of the fault, but also the input output values. So, what we actually mean is that the basic data structure we are trying to use here is called a concurrent fault list. Now, in the concurrent fault list, the entries are typically of the form, of course, the fault, the input values of the corresponding gate where the fault resides, and also the corresponding output value. So, in addition to the fault, we are also storing information about the input and output values. Now, let us take an example to illustrate this concept. Suppose we have a gate, say a NAND gate, a 2 input NAND gate, which is being fed by some sub circuit. Well, so we are not concerned about which sub circuit. So, we are concentrating on this particular NAND gate. Now, let us say that the two inputs of this NAND gates are A and B, and the output is C. Now, presently in response to the applied input, also suppose that the input values A and B are 0 and 1, and the corresponding output value is 1. I am showing this like this. And also we consider that there are 4 faults that we are considering, because we are assuming that after fault collapsing some of the faults are getting removed, but just for the sake of the example we assume that with respect to the gate, there are two local faults we are considering, and the local faults are A stuck at 1 and B stuck at 1, and also there are some non-local faults. These non-local faults are, say, we just give some names alpha and beta. So, actually alpha beta are faults which are taking place somewhere inside these sub-circuits which are feeding A and B. The net effect is that if the fault alpha takes place, the value of A becomes 1, if the fault beta takes place, the value of B becomes 0. So, you remember this for the time being. Now, these are the 4 faults. Okay. Now, with respect to these 4 faults, see, we have simulated this circuit with the true values 0, 1, 1 at the input values. Now, if these faults take place one after the other, let us show it like this. Suppose the fault alpha takes place, alpha will make the input value A to 1. So, the input output values will now become 1, 1 and 0. Similarly, if the fault beta takes place, B will be 0. So, it will be 0, 0 and 1. And if A stuck at 1 fault is there, then it will again be 1, 1 and 0, and if the B stuck at 1 fault is there, it will again become 0, 1, it will remain 1 and 1. Now, this is typically shown in textbooks like this, that this is the original gate and these are the gates in the faulty circuits of relevance, that all those faulty circuits for which there is some change, okay, or the local faults of course we will have to consider, and the other faults for which there is some change in either A or B, okay. We show it like this, but actually in your simulator, when you are actually simulating this, you will be storing this in the form of a table. The table will look like this. The table will contain a column fault, then the input values, then the output value. These will be the 4 entries of the table, and you will be storing it like this: fault alpha, input is 1 1, output is 0, fault beta 0 0 1, A stuck at 1 1 1 0, B stuck at 1 0 1 1. So, actually although we express this diagrammatically like this, but during simulation with each gate there will be a fault list, and the fault list will look like this, it will be a table. Okay. Now, let us take another example to show that how this fault list can propagate from one gate to another, because this fault list is, it is not a static thing. We are creating the fault list for one applied vector. Now, if the input vector changes, we will again have to recompute the fault list, and again since this is an activity driven simulation process, we will not be simulating the whole of the circuit, but rather we will be simulating only those portions where there are changes, exactly like the method of deductive fault simulation. So, let us see how we do this. Here again let us take a very simple example for the sake of illustration. Say we have a NAND gate with the inputs A and B. The output of this is feeding another NAND gate whose other in this line, let us call it C, and this input is D. The output is say Z. Okay. Now, at any given point in time, suppose the input applied logic values are 1, 1, so the output will be 0, and D is also 0, so 0, 0 and 1. Okay. And also consider that here the faults that we are considering, of course, we will be considering the local faults. Local fault means faults at lines A, B, C and D, but in additional in addition to this, we will also be considering some non-local faults, just for the sake of illustration, that in the fault list also the non-local faults may appear. So, here also we consider that there is a fault alpha whose effect is to make the line B equal to 0. There is another fault beta whose effect will be to make the line D equal to 1. So, alpha is a fault which is affecting B and beta is a fault which is affecting D. Okay? Fine. Now, under this condition, let us see what the fault lists would look like. So, I am showing the fault list in the form of tables. For this gate, the fault list will look like this. We just express it like this. Well again we just also consider that after fault collapsing, some of the local faults have been removed. So, the local faults that we have to look at are A stuck at 1, C stuck at 1, D stuck at 1, these. Okay. So, for this, the fault list will consist of A stuck at 1, this is one local fault. We write it like this, this is the fault, this will be the corresponding input because it will remain 1, this will be the corresponding output. Similarly, alpha is a fault which can affect this gate, which will make B equal to 0. So, alpha, now the input will be 1 0, the output will be 1. So, this is the fault list which is associated with the first gate. Similarly, the fault list that will be associated with the second gate, it will look like this. The first local fault will be C stuck at 1, this will make the inputs 1 0, output will be 1. Then D stuck at 1, 0 1 1. Then the fault alpha, well here this fault alpha, when you are calculating, you will have to make use of the fault list of the predecessor gate, because you know that if the fault alpha takes place, the output is 1. So, this 1 will come here, it will be 1 0. Similarly, the fault beta will make it 0 1, this will also be 1. So, if Z is the primary output, you observe one thing, that since the fault free output was 1 and in presence of all these faults the output is also 1. So, for the presently applied input vector, none of these faults are detectable. Okay? Fine. Now, suppose we change the inputs. Inputs we change in such a way, say the value of A which was 1, it now becomes 0. We change it from 1 to 0. So, as it changes from 1 to 0, the output of this gate C will become 1. So, this value which was 0, the true value, this will now become 1. Okay. So, after this change, there will be some modification in the fault list. So, let us see how this will get modified. This fault list will get modified as follows. The modified fault list will be A stuck at 1, this will again remain 1 1 because A is stuck at 1, 0, this will not change, but this alpha will change, 1 0, it will now become 0 0. Similarly, for this fault list, the modified one will be A stuck at 1. Well, now A stuck at 1 will come because for A stuck at 1 fault, the output is supposed to be 0, which is different from the current applied logic value. So, this is a logic event. Okay? The value of the line in presence of this fault A stuck at 1 is different from the true logic value, which is now equal to 1. So, that is why A stuck at 1 fault will also appear in the fault list now. So, for this will become 0, this will also be 0, because A stuck at 1 will make this line 0. Okay? So, 0 0 1. Similarly, C stuck at 1 will remain 1 0 1, D stuck at 1 will also now make it 1 1, output will be 0, and similarly beta will make it 1 1 and 0. So, now you see that the output was still 1, but there are 2 faults now in this list for which the output is 0. So, these are the 2 faults which will get detected by this second test vector. So, actually this is a very small example I have illustrated, but this procedure can be applied to much bigger circuits as well. And as you can see, this method is very similar as compared to deductive fault simulation. There also we propagate some fault lists, but in deductive fault simulation we do not simulate the gates when we inject the faults, rather we try to compute the fault list using some set theoretic rules. Okay. So, for concurrent fault simulation, if we want to summarize, well, it runs faster in general as compared to deductive fault simulation, because in deductive fault simulation you have to carry out some set theoretic operation based on strings which are typically slow. But the problem is that since we have to store bigger fault lists here, memory requirement is higher, and of course, it is also unpredictable just like deductive fault simulation. Okay. So, we have talked about some of the algorithms for fault simulation. So, just to summarize once more, fault simulation is used to ascertain or verify the quality of a set of given test vectors. We want to find out what are the faults that are getting detected, what are the faults that are not being detected, we have to detect them, and a related figure of merit that we get is called the fault coverage, the percentage of faults that are getting detected. Okay. So, now we very briefly look at the problem of test generation, because the test generation algorithms which are used are fairly complicated, and we are not going to discuss the algorithms in detail, but rather we try to give you the basic idea. Okay, the process of test generation is basically this: given a circuit, a netlist and a fault list. So, you have a circuit with you, you have a fault set. This fault set can be a collapsed fault set. After this fault equivalence and dominance collapsing, you get a reduced fault set. So, of course, this fault set have been obtained under an assumed fault model, typically the stuck at fault model. Now, the test generation process would help you to determine the set of test vectors which are required to detect the faults in this given set. Well, it can also tell you that for some of the faults it is unable to find a test vector. So, it will also give you the list of undetected faults. Now, let us try to see for this what are the things that are actually required. Okay. The first thing is to set a reverse logic value at the site of the fault. Like what I mean to say, let us take a simple example. Let us take a simple circuit like this. Suppose we want to detect or we want to find a test vector to detect a stuck at 0 on this particular line. Now, the first requirement for detecting this fault is that you will have to excite this particular line with a reverse logic value. Now, since this is the primary input, you can straight away apply a logic 1 to this input and justify the primary inputs is required if there is an internal line. For example, if we were considering a fault say here, a stuck at 0 fault here. Now, in order to apply the reverse logic value 1 here, we will have to trace back and find out that well we have to apply 1 1 to this AND gate. This is called justification of the primary inputs. Okay. So, in order to apply the reverse logic value, we have to trace back if necessary and we will have to apply the corresponding input values. Not only that, we will also have to set some values to the primary input, so that any change on that line will get propagated to the output. Like for example, if we again consider this stuck at 0 fault model, well, I am applying a logic 1 here, fine, but suppose to the other AND gate I had applied 0 0, then this output gate will be 0. Then any change out here I will have to apply a 1 on the other input also, so that any change out here will propagate here, and since this input is 0, this change will also go to the output and we can detect. But suppose I have applied 0 1 here, not 0 1, 1 1, 1 1. So, since this is an AND gate, the output will be 1, and irrespective of what is happening in this gate, the output of this OR gate will be 1, and this fault cannot be detected. So, we will have to apply suitable logic values to the gates, so that the changes are propagated to the output. So, we will just see with an example how this is done. In fact, in practice there are a number of test generation algorithms which have been developed. These are some of the classical ones, but after that there are many modifications and improvement which have taken place. Boolean difference method, D algorithm, PODEM, FAN. So, there are a number of such algorithms. Now, all these algorithms, well, other than Boolean difference, this is an algebraic method. All these methods try to do or try to carry out a process which is called path sensitization. So, let us try to understand what is meant by path sensitization. So, as we had illustrated with that small example, that we need to do or carry out 3 steps. Fault sensitization means applying the reverse logic value at the site of the fault. Fault propagation means we have to find out a path through which the fault will propagate to the primary output. And line justification means in order to do that, we will have to apply some suitable logic values to the other lines of the circuit. So, we will have to do that systematically. Okay. So, let us take an example to illustrate this, how we do this. Okay. Let us take this example. This is a small yet an example with some complexity, because there are fan outs. Just to observe one thing, this circuit has a structure which in terms of testing is considered to be a complex structure. It has a fan out and also it has reconvergence, that means the fan out branches are finally merging into a gate down the line in this OR gate. So, this is called reconvergent fan out. Okay. So, in this example, these are the primary inputs A, B, C, D, F, G are the fan out branches, H, I, J, K, L, these are the lines. And suppose we are trying to detect a fault stuck at 0 on the line B. Now, we would be using some notation. Well, what we want is that any change on the line B should be observable as a corresponding change on the primary output. This is stuck at 0. If I apply a 1 on B, the output value which was there for the good circuit would change. So, just by observing the output, I could say that the fault B has occurred or not. Okay. So, notationally we denote the symbol D as a change. Well, D, it does not matter whether it is 0 to 1 or 1 to 0, D indicates some change. Well, as a matter of convention, let us say any 0 to 1 transition on a line, it can be denoted by D. D is a change. So, D bar will denote the corresponding reverse change. So, D or D bar means that some change is going on that particular line. So, when we talk about a change, we are actually talking about change with respect to the good circuit. For the good circuit, the line had some value, and when the fault occurs, the line is having some other value. Okay. So, this we denote by D or D prime, fine. Now, in this circuit we want to detect this fault. Let us try the first alternative. The first alternative is that we try to see that if we can propagate the fault through path FHKL. Let us try this path, whether you can propagate this path, this fault through this path. Okay. Let us see it. So, we are trying to propagate it through this path F, H, K and L. Okay. In order to propagate this, let us see the condition. Just to observe, if it is an AND gate and if you want to propagate a change on one of the inputs, the other input value must be set to 1, because if it is set to 0, the output will be permanently 0. Similarly, if it is an OR gate, if you want to propagate a change on one input, the other input must be set to 0. Similarly, for NAND and NOR. Okay. So, these are the rules which you have to keep in mind. Now, we have to propagate this fault through this path. Since this is an AND gate, I must apply 1 on the other input. There is an OR gate down the line. So, I must have a 0 on the other input. There is an AND gate. In order to propagate this, I must have a 1 here. So, these are the requirements. I must have 1, 0 and 1 at the other inputs of the gates which are falling in the path. Out of these 3, A and E are not an issue at all, because these are primary inputs. I can always apply 1, 1. But let us see if we can have a 0 on J. This is a NOT gate. If we want to have a 0 here, if you do a back trace, this means that you need a 1 here. Now, this is an AND gate. If you need a 1 here, you must have C1 and also G1 permanently. But this is the site of the fault. If the fault is there, then G will be 0 and this line will no longer be 1, this will be 0. So, in presence of the fault, you cannot propagate the fault, because in presence of the fault J will be equal to 1 and the fault will get blocked here, the fault will not get propagated. Okay. So, this example shows that this line justification in order to propagate the fault may not be that easy a task. It is very difficult, it may need considerable searching across the different paths in the circuit. Okay. So, now let us try another alternative. Well, instead of trying the path FHKL, let us see if we can excite 2 paths together. Concurrently, we can propagate the fault through the 2 paths. Now, here you observe one thing, the change here we were indicating by D. So, D through an AND gate, there is no inversion, 0 to 1 becomes 0 to 1, D, D and D. There are no inversions in between, no NOT, NAND and NOR. So, D does not become D bar. So, any 0 to 1 change here will be reflected as a 0 to 1 change here, 0 to 1 here and 0 to 1 here, they all remain D. Now, at the next attempt, we try the paths FHKL and GIJKL simultaneously, which means the first path we try is this and the other path we try is this. So, now let us see what is the implication. This is the site of the fault. Now, if we want to excite both these paths, okay. So, first thing is that I have to apply a 1 here to this AND gate, I have to apply a 1 here again. Okay. Now, this is stuck at 0, I have to apply a 1 here. So, actually this point I am applying a D. So, D on F, D on G. Since we are applying 1 here and 1 here, so D will also come out here and here. This is an inverter. So, to the output of the inverter we get a D bar. Now, you observe one thing, you have an OR gate, one of its input is D, the other input is D bar. What does this mean? That this input is going from 0 to 1, the other input is going from 1 to 0. So, in the first case the inputs were 0 1, other case it were 1 0. So, in both cases the output will be 1 and output there will be no change, output will be permanently at 1. So, in this case the two paths are mutually masking each other, they are cancelling out the effects, with the neat result is that the fault is not getting propagated beyond this gate. Okay. There will be no change on K and hence no change on L, right. So, if you try to propagate the two paths together, it is also not possible. Now, let us look at the last alternative, where we will find that in fact we can find out a solution, that we just look at propagating through this path, single path, the other path. Now, you look at the gates which you encounter, this is an AND gate, so you have to apply 1 here, this is an OR gate, we have to apply a 0 here, AND gate you have to apply a 1 here. Now, this is an OR gate, in order to apply 0 here you backtrack, but you cannot apply a 0 here because you are affecting a change here, but the other input you can always apply a 0. This is an AND gate, if you apply a 0 here, this will always be 0. So, this is possible. So, now with respect to the D propagation, here it was D, output of the AND was also D, output of the NOT gate is D bar, OR gate other input of 0, so the output will also be D bar, and one input at 1 is also D bar. So, here we have at last found a test. 0 1 1 1 is the corresponding test vector for detecting the fault B stuck at 0. So, you see that this is a very small example, yet we had to explore so many paths and possibilities before actually successfully finding a path. So, this is a problem you will have to remember, that in general when you have a circuit of much higher complexity, much bigger circuit, much larger number of gates, doing this kind of deterministic test generation may sometimes be very expensive in terms of computation time. So, people have explored other alternatives as well. Well, I am stating one alternative here, but exactly how this is done, this we will be discussing later. This alternative is something called random pattern testing. Well, actually it is not purely random, you should call it pseudo random, because these patterns are generated using some algorithm and the same pattern can be repeated. That is why it is not truly random, it is pseudo random. In case of random pattern testing, the idea is that, well, I am trying to first explain you with the help of a simple example. Suppose you have a circuit under test, these are the inputs, these are the outputs. Now, instead of deterministically generating the test vectors to detect the faults using a test generator algorithm, it has been found that if you simply apply pseudo random patterns in the inputs, blindly apply random patterns, then for most of the circuit a pattern like this holds. Here if you plot number of patterns you apply, and here fault coverage, then typically the curve looks like this. So, this may be the point of 100%. You will find that say for example, you apply 200 patterns, you get a coverage about 85% or so. So, what people do is that they sometimes use pseudo random patterns as the first few test vectors, they do not use any deterministic algorithm, just generate them, and using fault simulation they find out what are the faults that are getting detected. Now, after doing this for certain number of patterns, they will find out that what are the faults that remain to be detected and finally, they use the test generator algorithm to detect those remaining faults. Okay, fine. So, if you just look at the overall flow of this random pattern testing, well, this is an optional step, set input probabilities. If it is a pure pseudo-random pattern, the probability of a 0 or a 1 appearing on the inputs are all 0.5. These are the input probability, initially they are all half 0.5. You generate a random vector, simulate faults to find out how many faults are getting detected, you check the coverage, if it is inadequate you go back. Well, you either do this or you do this for a fixed number of times. Okay. This is an optional step, as I told you, not all people do it. If you find that the fault coverage is not improving beyond a point, you analyze the circuit and the faults that are yet to be detected and change the input probabilities. There are ways of changing probabilities, we would talk about this later, and by changing these input probabilities we can actually generate pseudo-random patterns where the probability of a 1 and 0 appearing are something other than 0.5. There are ways of doing that. So, actually pseudo-random testing is a very interesting method, because well, the first thing is that I have shown this plot that you can simply apply pseudo-random patterns and you can estimate the fault coverage. Not only that, there are some other advantages, like pseudo-random pattern generation. This can be done very efficiently in hardware. This is another big advantage. This is practically done using a simple hardware structure called linear feedback shift register. Or LFSR in short. We will see later that how an LFSR looks like and what are its properties, but actually the thing is that you can use an LFSR simply to generate the pseudo-random patterns and to detect the first few number of faults, in fact first many number of faults. So, the faults which remain to be detected will be detected later by using test generator algorithms. Okay. Now, the example that we had taken earlier for test generation was for a gate level circuit. Now, in fact, most of the modern day test generator algorithms or tools, they work for gate level circuits, and some of them also work for mixed level circuits, where some of the netlist, a part of the netlist may be in terms of gates, there may be some other blocks like multiplexers, decoders, ALUs and so on, a mixture of those things. But very recently another school of thought has emerged. Many companies or industries, they do not want to spend much time and effort for this test generation at the gate level and fault simulation. Rather, they look at the functional blocks at a high level and try to generate tests for them. For example, an adder, for example, an ALU, a decoder. But there are some problems involved there. I will take an example to illustrate what are the problems, because if you generate tests at a functional level, at a high level, you cannot have a good, you can say you cannot have a high confidence regarding fault coverage in terms of the faults that are taking place actually inside that functional block. You are only talking about input output behavior. We will take a simple example to illustrate this problem, what this is all about. So, actually we are trying to compare functional automatic test pattern generator, ATPG is a term which is used, automatic test pattern generator versus structural ATPG. Okay. Now, the example that we are taking is a 64-bit adder, and just to keep things simple, we assume that this is a ripple carry adder, just for the sake of illustration, which means there are 64 full adders which are connected in cascade. Okay? Fine. So, the 64 bit adder will look like this functionally. This is an adder, this is the input A which is 64 bits, input B 64 bits, a carry in, sum will be 64 bits and a carry out. So, if you treat it as a black box, there are 129 inputs and 65 outputs. Okay? Fine. Now, we also consider the other alternative, that instead of treating it as a black box, we consider it as a ripple carry adder, where there will be 64 full adders which will be connected in cascade. Okay? There will be 64 full adders connected in cascade, and each full adder will have a sum circuit and a carry circuit. So, there will be 64 such blocks, and we can have a gate level netlist for each of those blocks. Okay? This is the other alternative we can explore. So, in the other alternative, you know, this sum circuit looks like this. Sum is the exclusive OR of AI, BI and CI. This is the sum circuit of a full adder. So, if exclusive OR gate is available as a basic gate, then this will be the netlist, and after fault, you can say fault collapsing. For XOR gates you cannot do much fault collapsing. So, there will be 10 stuck-at faults possible in each individual sum circuit. Okay. Similarly, if we look at the carry circuit, for the carry circuit is AB or BC or CA. So, for the carry circuit, this will be the realization in terms of AND and OR gates, and using fault collapsing and fault equivalence dominance collapsing, you can reduce the number of faults. So, it becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So, for the carry circuit there are 17 stuck-at faults. So, what does this mean? This means that at one extreme we have a realization which is a black box realization with 129 inputs and 65 outputs, and in the other extreme we have 64 full adders connected in cascade. These are the full adders 1, 2 and 64. So, each of these will be having 3 inputs and one sum and one carry will be going to the other one. Okay. So, it will look like this. So, the first one, the carry will be coming from outside. This is the carry in. Okay. Now, if we can come back and look at the number of faults that we are talking about, for the sum circuit we had said there are 10 stuck-at faults, for the carry circuit there are 17 stuck-at faults. So, there are 27 stuck-at faults. So, with respect to the gate level netlist, inside each of these there are 27 possible stuck-at faults. Okay. So, this is the scenario. So, now let us compare these two alternatives. What is the complexity of test generation? See, the first alternative, the functional test pattern generator, well, if you treat the whole thing as a black box, then nothing will give you confidence, well, unless you apply all possible inputs and see the outputs, because you do not know that which subset of input to apply in order to test it. Okay. But in this case, applying all possible input is simply out of the question. Why? there are 129 inputs, of course 65 outputs. So, if you want to apply all possible inputs, it is 2 to the power 129, which is a number so large. And even if you assume that you can apply 10 to the power 9 patterns per second at the rate of 1 gigahertz, still it will take you 2 into 10 to the power 22 years to apply so many patterns. Okay. So, just using this blind kind of a functional ATPG is simply out of the question. So, what people normally do, they use this functional ATPG with some kind of an intelligence, some kind of an intuitive, you can say, experience regarding what kind of faults that can occur in the circuit and what kind of functional behavior you can expect in the presence of faults. So, based on design experience, they try to design the input test set. Okay. Fine. Now, the other alternative, if you go for structural test, now in the adder circuit, in the ripple carry adder, we had said that each full adder stage will have 27 faults. So, there are a total of so many faults. So, just assuming that each fault will require one test, well, in general one test vector can detect more than one fault. So, it will be less than this. So, even assuming that one test will detect only one fault, so you need only 1728 test vectors for this single stackered fault model. So, on a 1 gigahertz ATE, it takes about a microsecond. So, you can see that this is a very practical way of handling the problem. If you treat the circuit as a gate level, even your time for testing gets drastically reduced. So, in practice what people do is that designer initially gives a small set of functional tests, like for an adder it tries to find out, it tries to give the input that one of the input is 0, other is something else. What happens? You give some input so that there is a carry, you add the two maximum numbers, all 1 patterns. These are some of the intuitive inputs that the designer gives. So, in addition to that, you use some structural tests and try to boost the fault coverage as high as possible. Typically, the industry people will be happy with a fault coverage in the tune of 98 plus. Now, this simple example will give an idea that this functional test, although it is good, it can sometimes require enormous amount of time and effort in order to generate the test vectors. Okay. The next point that we want to address is that, well, whatever we have discussed so far, the example illustration we have given, we have taken only for combination circuits, but all practical circuits are sequential in nature. There will be some storage elements like flip flops as well. So, if we have the storage elements in them, the complexity will also go up accordingly. So, our next topic of discussion would be how to address the problem of testing sequential circuits. Well, there are ways of generating test vectors for sequential circuits, but they are much more complex as compared to the combinational test generation problem. So, what normally designers do there is something like this. See, you have a given circuit. See earlier what happened, the designer and the test engineer, these were two independent teams. The designer designed a circuit or a chip, they gave it to the test engineer, and the test engineer's task was to test the chip. Now, as the complexity of the chip is increasing, the number of components divided by the number of pins, that is increasing day by day. So, the task of the test engineer is becoming more and more difficult. So, now what happens, the two teams very closely collaborate with each other. The test engineers provide some inputs to the chip designers in the sense that they say that, well, here are some of the design rules which we would want to be incorporated in the designs that you come up with. So, if you follow those design rules, then the final product that you get, the chips, they will be such that it will be easier for us to test. So, there is a philosophy called design for testability which has come up. Now, in our next lecture we shall be trying to discuss more on the design for testability issues, the different techniques and ways people go about doing it in some detail. Thank you.